to get started. Okay, it looks like we are now live, and I'm going to be walking through how to perform a power analysis in R. If you have any questions, make sure to give me a shout out on Twitter. I'll be checking the Twitter stream just to see what's been going on. I'm also looking after the wife is out tonight, so it is me and the baby. So if the baby starts crying, I'm definitely going to have to go because it's always family first. So what we're going to be doing is looking at power analysis within R. So we have the R Studio up here. And first, we'll basically go over what power analysis is. And a power analysis basically tells you the probability of observing a statistically significant result given a specific sample size, an alpha level, that is your p-value, and the effect size that you expect to get. So in other words, hypothetically, if you were working with an 80% power, and you hypothetically were running 100 studies, 80 of them would be significant and 20 of them wouldn't be. This is really important because there was a study that came out a few years ago from Kate Button and colleagues, which found that within neuroscience at least, power in those studies was hovering around 10 to 20%. And that's pretty similar for most fields in the biobehavioral sciences. So there's a definite need for researchers to better understand how to better power their studies. Now, at the moment, we do have G-Power, which is a free bit of software, which is point and click, and you can perform your analyses there. But some of the terminology in the software is quite confusing, and the documentation is also quite confusing unless you read very carefully. And the other thing about G-Power is it doesn't actually lend itself to reproducibility. In theory, you can copy and paste the power analysis output and put that as, say, a supplementary text file in your analysis, but I've never seen anyone do that, even though it's possible. However, if you're doing your analysis in R, you are able to actually easily export your R script, so others can recreate your analysis and easily see what you're doing with your analysis. Okay, so basically, like I said before, when it comes to power analysis, if you have these three parameters, that is your participant numbers, your alpha level, that is your p-value, and the effect size you expect, you can calculate your power. But within these four parameters, these are all interrelated. So if you know any three of these parameters, you can calculate the other one. And this is how we can actually use power analysis to determine the sample size that we need. Because if you have your statistical power, if you have your alpha level, and then if you have your effect size, with those three things, you can determine the sample size that you need a priori for when you are designing your studies. Okay, so let us kick off and do this in R. And the first thing we're going to do is we're going to load the power package. It's spelled PWR. Okay, first thing. Let's do that. We're running that. Okay, so we are good to go. Now, one thing that is really handy is actually opening up the help file to see how to do these analyses, and these things are easy to refer to. So one way that we can actually open up the help file is we can scroll down in the package list. As you can see, I've loaded a lot of packages. Some of them I've probably only ever used once. Okay, so we click on that and we can see the documentation. So the first thing we're going to do is look at the power test for correlations. Okay, so I'm just double checking to see if there's any questions so far. Probably not. Okay, here we go. All right, so basically we are looking for calculating power for a correlation. So we can see here in the usage bar, just checking that it's all going good. Yep. So we can see here in the usage bar, this is how we this is the function, or these are the terms we put in the function to calculate these things. And like I said before, if we know any three parameters, we can calculate the fourth. So here are the parameters here for calculating, for doing a power test for a correlation. N, which is your number, significance level, which is typically set at 0.05, but you can change this. Your power level, and your R, which is your effect size. So what we're going to do is we're going to create an object, and we're going to call this power. Okay, so let's do this, power R test. Okay, so let's just say we are interested in getting an effect size, or our effect size of interest is an R of 0.3. Before we do that though, I do want to show you a little thing that you can actually do within the R package, which is a way that you can look at the Cohen's effect sizes. Now, there are a few things that aren't great with Cohen's recommended effect size, which I'm going to go into in a couple of minutes. But just to show you around the package, I'm going to show you something here. So what we can do is with Cohen's conventions, basically with the Cohen's conventions with typical tests, there are what are considered small, medium, and large effect sizes. So if you want to actually figure out what these are, rather than referring or Googling it, you can actually look at this within the package. Like I said, there are problems with this, but we'll get back to that. So let's put this in. Cohen. ES test equals, in this case, we're looking at R, and size equals, I'm going to be realistic here, so we're going to go with small. I'm going to run with that. Parentheses, course, sorry, quotation marks. There we go. So a small effect size is 0.01 in this case. So we're just going to move this up the top here. Okay, so what we're going to do here is we're going to go back, keep a peek at this, and see. Okay, so we're going to put in the R equals 0.1. Next thing we're going to do is put in the significance level. Now we're going to go with 0.05. Of course, there's a lot of debate as to what significance level you should use. Some people are saying 0.005 to redefine statistical significance. Others saying that you should justify as well. I'm not going to get into that debate, and we're just going to go with 0.05, but we might do 0.005 just for illustration's sake. Okay, so we've got significance level and power. We're going to go with 0.8, which is in many circumstances the typical power level that a lot of people use. Some departments or some ethics committees or some research schools go with 0.9. Other fields go with 0.99. But a lot of people, at least within the biobehavioral sciences, go for a power of 0.8. So we're just going to go with that here. Okay, so we are calculating this. Just going to check if there's any. Okay, here we go. Getting a few comments now. Keep them coming if you have any questions. All right, so calculating R power into this object here. There we go. Okay, so assuming we're interested in an effect, or we expect an effect size of 0.1, and we are going to be using, or we're using a significance level of 0.05 and a power of 0.8. Here we go. We would need 782 participants. Wow, I hope you are well resourced if you want to do that. But, okay, so here we have the results down here, which is nice and which is extremely clear, and it sort of tells you exactly which parameters you put in as well. For argument's sake, let's see if we go. Okay, so what happens? Look at the medium, which is 0.3 from memory. Yep, 0.3. Okay, put this in. All right, so before we had 782 participants. How many do we need here? All right, 84. Wow. So it's incredible. If you're anticipating a medium effect size, you are going down to the participants that you need down to 85 based on the small one, which is 780. So it's incredible how much these things change. Okay, let's go for large. See what comes here, 0.5. Run that. All right. 29. So if you're anticipating a large effect size or a large relationship between two variables, then you only need 29 people, which is a huge difference from 782. Okay, so what happens if we want to redefine our statistical significance to 0.005? Of course, this changes. So here we had 29. Run this again. And we have 47. So things change when you change the parameters, because these things are all related. Say your ethics committee demands or requires you to have a power level of 0.9. What happens here? Run this again. 38. So things obviously need more participants if you are after more power. Now, there's a lot of debates as to how much power is appropriate. Once again, this is another thing you should probably justify, but I'm not going to go into that today. Okay, so now we are looking at that with R. So, and the other cool thing you can do as well. Okay, so let's go back to 0.3, which is medium, 0.5 significance level, and a power of 0.8. The other thing you can specify with here is whether your test is two-sided or one-sided. If you are pre-registering your hypotheses or pre-registering your study, and you expect your effect to go a particular way, what is much more efficient is to actually calculate power based on a one-tailed test. And you can do that. So let's put this in. Alternative. Okay, the standard, if you don't do anything, is two-sided, but you can still type it in. So this is going to be the same. Okay, so let's run this. Okay, 85. But let's say we had a specific one-tailed hypothesis, then, and you think it's going to be greater than if it's one-tailed test, we go from 85 to 67. So if you pre-specify your hypotheses and you have a good idea, or you're predicting a particular direction of an effect, it's much better for your resources if you specify in your power analyses that it's going to be a one-tailed test in the direction of the test, and then you can do this within the power package and specify that. So that's a really cool feature. So all you need to do is change the alternative either from two-sided to greater or to less. That is a really really cool feature. Okay, now let's have a look. So that is how to do it for a correlation, remembering that you can change and manipulate all these variables to calculate what we want. So it's going to have a look to see if there's anything there. Okay, let's continue. Like I mentioned before, any questions, please let me know on Twitter. That is the best way to get in contact, and perhaps I can answer it live. We'll see how we go. Okay, so that is here's another cool thing you can do. You can actually plot and visualize what this how things change as you change these parameters. So we can put plot R power, which is the object that we created. We can plot this. Something's happening. ggplot is doing its thing. There we go. All right, let's zoom in. So this is a plot that you can actually use, which looks at how power changes as a function of sample size. Here it actually notes that the optimal sample size when it comes to getting 80% power is 67, but you can see how this thing changes as a result or as a function of sample size. So here's a very nice visualization. So for instance, with this particular design, if you had a sample size of 25 participants, you would only have power of 40%, say. So this is a nice thing you can do, and it's really easy to do. All you need to do is put and do this plot function. All right, that is all for correlations. Let's have a look at t-tests, another common thing. Okay, power t-tests, so we can have a look at the usage. Okay, so what we can do is let's create another function. Sorry, create another object. Power t test. Okay, so let's say, for argument's sake, we are interested in a Cohen's d of 0.2. Okay, and we're going to go with significance level of 0.05 because we're being conventional, and a power of 0.8 because we're being conventional. And by default, it is a two-sided test, so we're just going to leave it like that. Let's type it in now. Alternative equals two-sided. All right, let's run that. See if this works. Cool. The other thing we want to do is actually specify the type of test, of course, the type of t-test, because there's a few you can do. So what we're going to do here is a typical, well, usually typical 2 sample t-test from 2 different populations of people. Okay, let's run that again. Oh, we forgot the comma. There you go. Error. Put the comma in. Good. Okay, now, what I love about the Power Package is that it's very clear about what the n means. Here you can see it says that the n is the number in each group. Just checking this. Yeah. So the n is the number in each group. So here we need 394 people in each group, and that's pretty big. But a Cohen's d is typically considered quite a small effect size. So in order to actually detect a significant effect with a small effect size or a small anticipated effect size, you would need almost 400 people with a 2-sided test. But what happens if we jump that up to 0.5? Or we anticipate 0.5, for instance. All right, 64. So that's a little bit different. Okay, so let's bring that back down to say 0.3. Okay, so look at that. And we have, 176. All right, so let's just say you're pre-registering your hypothesis and you believe the effect is going to be going in one direction. As always, you can change the alternative, and it goes from 176 to 139. So it's a little bit better if you have a pre-registered directional hypothesis there. Okay, let's just change that back to sample. And obviously, as before, if you're changing your significance level and your anticipated power, these numbers are going to change. Okay, so now that was for a 2-sample test. We'll just run that again. Alternative shouldn't be 2-sample, it should be 2-sided. Okay. Run that again, 2-sided, typical test, and we have 176. Okay, so let's change from a 2-sample t-test to a paired t-test. These designs are much more powerful because you need fewer participants. In many cases, it is a bit of a pain to invite the same person to come back again, but it is a better use of your resources. Let me show you why. Let's change the type to paired. Oh, what's going on there? Yeah, I can't type. All right, remember, 176. Do this again. Paired, 90. Wow, look at that difference there. If you change your research design to go from a 2-sample t-test or 2 different populations to a between participant test to a within participant test, when it comes to your power calculations, you don't need to do as many. And that is fantastic. Look at that. That's a massive difference. And let's say you have a directional hypothesis. Imagine that. And we go greater. So we're down to 90 participants. Directional hypothesis. We're down to 71 participants if you pre-specify your hypothesis and you're doing a paired samples t-test. Okay, let's now, so that's 2 of the major things that you can do with the t-test. Before we go to the ANOVAs, just going to have a look to see. All right, now let's go back, as always, referring to the help file, power ANOVA test. Okay. Let's make a new function. Sorry, a new object. Power ANOVA test. Okay, so number of groups. Let's go with 3. We are interested in 3 different groups for a one-way ANOVA. Now, keep in mind that at the moment, the Power Package can only deal with one-way ANOVAs, not anything more complex. I do know that Daniel Larkins and Lisa DeBryan are actually working on a package that allows you to do or calculate power for more complex ANOVAs, and I'm going to link to that, which is still in development. I don't think it's ready for prime time yet, but the development version is up on their GitHub page. But apparently in a few weeks, it's going to be ready for the big time. But for now, I'll show you how to do power analysis for a one-way ANOVA. Okay, so we got 3 groups. Our effect, let's go for like a medium-ish one of like, or conventionally medium one of 0.15. Significance level, 0.05, power, 0.8. Okay, so how many, let's run that. All right, so we need 144 per group. That's quite a lot. Say you're only doing 2 groups, or actually no, let's go with 4 groups. Keep things interesting. 143 per group. What happens if we have 4? 122 per group. So a lot of participants. As always, we can plot and see how this looks like as a function of sample size. So there we go here. Okay, here we go. So given that you have 4 groups and this is the effect size that you anticipate, 123, and this obviously the fewer participants you have, the less power that you're going to have. So it's a handy little plot there. Okay. So we have these 4 ways, or we have these 3 ways of calculating power. We have correlations, we have t-tests, and within that we have pair t-tests, and between participant t-tests, and we also have one-way ANOVAs. Here I've been using Cohen's conventions for how to calculate power, but that is not necessarily the best way. So really the next natural question is how do you determine what effect size you're putting in these calculations? What a lot of people do is they use pilot data. They'll run a small experiment, say with 20 people, and look at the effect size that they generate there and use that to power their main study. But this is biased, and this is actually going to create inflated effect sizes, which is going to create which will lead you to calculating inaccurate sample sizes. So I wouldn't do that. I'll link to a paper which demonstrates why. The other thing people do is they choose a single prior study. It may have been a study in their lab, or it could have been a study from elsewhere, but they'll look at this study and they'll calculate the power in the study, and based on that they'll use that to power their study. Now this is also something else which is quite which has a lot of potential to be biased. Of course, we all know the problem with publication bias, where null results tend not to be published, and even results that are published, effect sizes, given researcher biases, tend to be inflated. So given this risk of effect size inflation, then using this as a way for your effect sizes is potentially going to inflate the effect size and reduce the participants you need, but increase the chances of actually inaccurately powering your study. Okay, next thing you can do, or next thing a lot of people do, is they use Cohen's conventions. This is built into the package, and I think most people, when they're justifying their sample size calculations, they either go by, we did a pilot study based on this we looked at a prior study, or we used Cohen's conventions. Now, the problem with Cohen's conventions is that these are only ever designed to be a fallback when you really had no idea what effect size to use. Cohen chose a medium effect size because this is a difference that you could actually see, and these were his words, a difference that you could see with the naked eye, and coincidentally, these were also differences that were the average effect size across a given field. So say you had 100 studies which looked at a certain phenomenon, and the average or the median effect or the 50th percentile effect would be the medium effect size. And when you look at published literature, this tends to be kind of somewhat true, but of course the published literature is biased, so it's hard to see how accurate this is. So you have this median effect size which is used via Cohen's conventions, and you also have small and large effect sizes which are equidistant from each other. So typically say you have a body of work, effect sizes that are at the 25th percentile would be considered small effects, and studies that are at the 75th percentile would be considered large effects. But that's how Cohen calculated that. But of course, just because that's what Cohen calculated doesn't mean that's going to be relevant for your study. So you shouldn't be mindlessly using these effects because they may not necessarily apply to you, despite the fact that it's in the power package there. So I wouldn't necessarily recommend it, and the fact that a lot of people use it as well because it's not accurate for your field. So there's an alternative, and this is an analysis which I've done, which is looking at an effect size distribution. So say within your research field, well, firstly what I'll do is I'll walk you through a study that I did. Maybe I can actually get the figures up. No, we can't find that. Okay. So basically for this study, what I did was I looked at the field of heart rate variability, which is a non-invasive measure of parasympathetic nervous system activity, and looked at case control differences between patients, typically psychiatric patients, and healthy controls, to see what the effect sizes were like. And I was able to extract 300 effect sizes and look at the distribution of these effect sizes, and then calculate the 50th percentile for a medium effect, the 25th percentile for a small effect, and the 75th percentile for a large effect. And I actually found that 50 was actually, the medium effects was actually very close to an effect size of 0.5. So it was very similar, but there were slightly different effects for small and large effects. And a few people have done this for their own research fields. I think it's been done for personality measures. I think it's also been done, it's been done for, this approach has been done a few different ways, and I'll link to this approach. But the problem here is, like I mentioned before, published studies tend to be biased. So the effects that we're getting may actually be inflated. One thing that I did to potentially head this off was to look at publication bias, or basically look at the distribution of effects to see how many were around that effect size, around that significance level of 0.01 to 0.05. What I found was that there wasn't actually an overrepresentation of effects around this significance area, which to me at least demonstrated that there was a lower risk of publication bias. But we can never know that for sure. There are other ways of determining the risk of publication bias, such as p-uniform and p-curve, but I haven't done that for this body of work yet. So it is a little bit more informed than, say, using a single study, using a pilot test, or using Cohen's thresholds. But there is also a small potential for bias. So what do? We're still stuck. Okay, so ideally, the effect size that you want to include is the effect size that you want to show. That's a little bit frustrating because there's no easy formula here, and as researchers, we want easy formulas, but unfortunately, in this case, it doesn't exist. In some fields, these things can be clear. There are effect sizes that you are interested in. For instance, if you are looking at the effectiveness of a new treatment for depression, say, you might look at the percentage reduction in the Beck Depression Inventory, which is a popular test looking at depression symptoms, and typically a 50% reduction is seen as a response. So in that case, you actually have a very clear idea of what effect that you're interested in. But of course, in many fields, this isn't as clear cut. So you just have to think carefully about what effect size that you're interested in. And this also speaks to the importance of pre-registering, so you can actually justify that you've considered this previously. But also doing a registered report is another way, because you can get feedback from reviewers prior to the collection of data, and you can justify the power level that you chose. And your reviewers might go, "Yep, that's spot on," or they might go, "Nope, you need to try again. There's not that much evidence for what you were choosing." So that is a real big plus of registered reports, because ideally, or basically what can happen is that you can suggest, and you can have all the good intentions in the world, and you can look at an effect size, but a reviewer might go, "Sorry, that wasn't the effect size that I would have chosen," and they can reject the study. But with a registered report, what you can do is beforehand, before you even collect the study, all the reviewers agree for the effect size that you chose for your power calculation, and there's not going to be any problems like that when it comes to the review stage. So big plus of registered reports. Okay, so that's one way of doing, and the final way that I want to talk about is by looking and considering what your smallest effect size of interest is. So this is a new alternative, and this idea has been around since the 80s, but it's only really been sort of rediscovered, so to speak, within the past few years, at least within the biobehavioral sciences. The smallest effect size of interest. With typical p-value testing, there's no way that you can actually provide support for a null hypothesis or a null model. But what you can do with equivalence testing is that you can reject effects as large or larger than a smallest effect size of interest. Okay, so what do I mean by that? So what this means is, say you were doing a correlation and you would consider effects of 0.1 to be practically meaningless. With equivalence testing, you can actually rule out and you can see whether there was evidence to support the fact that effects were large or larger than 0.1, and you can look at and test for equivalence. So this is really handy. So one perspective when it comes to powering your studies is considering at what point would you consider effects not to be meaningful, and then you can power your study that way. So, for instance, you might think that an effect of a correlation of R equals 0.1 is for all intents and purposes meaningless, and you can power it that way. So, let's now look at a second package to do power analysis for equivalence testing. It's a little bit different. The calculation is a little bit different. You can't just put in a effect size of 0.1 to look at the power that you need in the power package. So what we'll do is we will load Toaster, which is the name of the package developed by Daniel Larkins. There we go. Okay, let's go to packages. Look at the documentation. Okay, so let's determine power for correlations. Okay. Create a new object. Okay, power tost alpha equals 0.05. Statistical power. Let's go with 0.9. I know that's what Daniel's local department asks him and his students to do, so I'll go with that. Okay, now you want to determine your lower bound as 0.1 because that is the effects at 0.1 or lower are essentially meaningless. And well, that's how we're defining it. And the high as 0.1. Okay, so there we go. Okay, we get a nice little script here, and it's saying the required sample size to achieve 90% power is 1,078. A lot of participants. Now, I just want to show you the equivalent for that to show you that you can't use a typical power analysis using the power package. Just plugging in effects of 0.1. So we go 0.1, 0.9. Okay, so there's a lot of difference there. 852 if you're just looking at powering your study to detect an effect of 0.1, but if you want to actually use equivalence testing and setting your bounds as 0.1, your low bound is 0.1, high bound is 0.1, then you're going to need a lot more participants. So, but regardless, I'm going to post some more links about equivalence testing as well. So I've just gone over using power for equivalence testing, but of course there's a lot more details for using this task. And I think it's really important because when it comes to psychological theories, we can't improve and refine them unless we can reject them. And equivalence testing provides a means to actually reject our theories. So it's something that that you should definitely look into for your analysis. So before I log off, I'm just going to see if there's anything there. But yes, any other questions, please hit me up. Thanks for joining us, and I'll be back again soon with another live stream. I don't know what I'm going to do, but this is fun, and I'll be back again. And yeah, hopefully I didn't miss anything. And any questions, please hit me up. Bye.